Okay, our goal today is to review limits, but I'm going to do a pretty high-end review. When we first introduced limits in Calc 1, they're probably the scariest things you've ever done in math because they're so different than anything else. And the one thing that you have to always remind yourself, a limit and a functional value don't have to have anything to do with each other. A limit is where are you heading, not where you get to. And so we start with really simple stuff usually, and we always start with the simple indeterminate forms. But I want to remind you, because this is where we're going, the next two lectures, which will be Wednesday and Wednesday, we're going to essentially, every type of limit that exists, we're going to explore it and attack it and so on. There are 6 indeterminate forms. And we say forms. An indeterminate form is not a value, because if your answer is 6, that's your answer. Your answer is 6. You don't say that's a form. The forms, and we usually use the bracket notation just so there's no ambiguity. We say, I have a quotient, and numerator and denominator are both tending towards 0. Neither one of them can reach 0 because 0 over 0 is not a value, it's a form. And we loved that one. That was probably our favorite one because that usually meant factor and cancel. Then there was the form where numerator and denominator both grow without bound, and we say it's the infinity over infinity form. And these are the 2 forms that we attack in Math 150 because we learn all of the algebra necessary to do both of those. And actually, we really do know all of the math required. Now, we are going to continue, and next day we're going to now attack the next 4, which look like this. I have a product of things. One of them is tending towards 0, and the other is growing without bound. By the way, 0 times infinity doesn't equal anything. It's an indeterminate form. The next one, I have 2 large quantities. I'm taking their difference, and they both approach infinity. Now, a lot of folks make the mistake of saying, well, everything times 0 is 0. No, 0 times a constant is 0. 0 times everything else is not 0. You can't multiply 0 times something that's undefined, for example. And then this one. And then the last 2, which are the most complicated 2, but probably the coolest, is I have an exponential one where the base and the exponent are going to 0. That's an indeterminate form. That's not a number. And then the last one is I have an exponential form where my base is approaching 1, but my exponent is growing without bound. And at first glance, you say, isn't that equal to 1? Well, I'll give you a hint. The single most important limit by far doesn't even have a period. The single most important limit, and you did this in Calc 1. It doesn't matter what letter of the alphabet I use. They just have to be the same. As n grows without bound, 1 over n approaches 0. So this base is approaching 1. My exponent is growing without bound. The answer is not 1. Does anyone remember what that limit equals? You learned this in Calc 1. Gads, people, you got to know what this limit is.
E. It's E.
E, yeah. I know that was terrible. Yeah, this is E. This is the most important limit that exists, period, because E is the most important number that exists, period. Yet it's of this form. Oh, the answer is not 1, is it? So make sure you're muted, guys. I hear a lot of background noise. So this is an example of something we're going to work with and prove and so on. So today, we're going to basically look at this one, possibly this one, and definitely this one, because we can handle those. And then later, we're going to look at those 2 because they require special techniques. If you have something of an exponential form, that usually means you're going to have an e and a natural log in there somewhere along the way. It's kind of unavoidable, and they require special techniques. So we want to review these, and I want to review a few things that you know, but you may have forgotten or haven't used in a little while. Oh boy, this eraser is not helping me out here. Let's see, this one's better. A little bit better. Okay. Remind ourselves the fundamental theorem of algebra. Now, if you have a good pre-calc class, which I'm finding they're getting fewer and fewer of them. Hold on, so let me tilt that just a little bit. Here we go. If you have a good pre-calculus class, then you should have spent, at least a month on this kind of stuff. But I find most people in pre-calc, they review how to graph lines, how to factor quadratics, really important stuff that you learned in pre-algebra and elementary algebra. And they spend the whole semester doing that. They don't spend a ton of time on trig review. They don't spend a whole lot of time on conic sections, exponential functions, logarithmic functions, the stuff that you actually need for calculus. But this guy here, I'll remind you, if I said I have p of x, p being just polynomial function, a n x to the n plus a n minus 1 x to the n minus 1, all the way down to a1x plus a0. The a's are real numbers. They are just coefficients. The subscript is so I can keep track with which exponent. N is a positive integer. Okay. So if n was 10, then I go 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, constant term, and so on. This is an nth degree polynomial equation. Polynomial means I can only have non-negative integer exponents. Technically, the last one would have an exponent of 0. Okay, that's it. That's what a polynomial is. As an absolute now, I can factor this into exactly n factors. Now, we reviewed this a little bit earlier when we talked, if you remember, and we talked about setting up for the partial fractions decomposition. We did this part here, but I want to remind you now. This is an absolute. There is no exception to this. An nth degree polynomial can be factored into exactly n factors. R's are called the roots of the polynomial. The R's do not have to be integers. They don't even have to be rational. They don't even have to be real. If my coefficients are real, then if one of the R's is complex, then it has a complex conjugate pair. So that's one thing we've been trained all our lives, that every time you have a complex number, a plus bi, you have the conjugate pair a minus bi that goes along with it. That's actually only true if the a's are real. If I allow the a's to be complex numbers also, yikes, we're not going to do that in this class. But if I allow the a's to be complex, then complex numbers don't have to have conjugate pairs, and this is really nasty. I'm not worried about that one. I'm worried about this one. So why is this so important? Well, you used your synthetic division in algebra, so you did things like this. You only looked at the first and last, and if you considered every quotient of an over a0, every possible quotient of the factors, then those were all of your possible rational roots. Oh yeah, then I use synthetic division. And as soon as I found one of the roots, then I have a degree one less. And when I could do that all the way down to a quadratic, then I was done. This is something you probably spent a lot of time, I hope, in pre-calc. It's called the rational root theorem. It's part of this. But one of the biggest parts of this is this. If I take a root, if I take R1, obviously, and replace with X, this quantity is 0. So if P of C equals 0 for any real number C, then what that means quite simply is that X minus C is a factor. This is absolute. This comes from something called the Remainder Theorem, which you learned, by the way, in Math 46 even. So that's what the whole synthetic thing was. That's why if you have a problem like this, let's say the question was, I want the limit as X goes to 3, we'll keep it really simple. X squared minus 9 over X squared, let's say minus 2X minus 3. Let's say I have something like this. This is a simple calc 1. This is quite literally day 1 calc 1. So you say, well, if I can evaluate this at 3, I will, because that means nothing weird's going on. So you always see if you can evaluate it first. If I put a 3 into the numerator, I get a 0. If I put a 3 into the denominator, I also get 0. So we say this is of the form 0 over 0. We do not put an equal sign here for one simple reason. If you write limit equals number, it means you're completely finished with the problem. Because you would never say my limit is 7 and the number 7 equals, that doesn't make sense. If your limit equals a number, that's the limit. So once I put in equals, that would mean I'm done. No, it tends towards this form, which tells me, maybe I can factor and cancel. But you see, I'm not very good at factoring. Well, actually, you don't have to be very good at factoring, because if I put a 3 into my numerator, and it causes my numerator to equal 0, then that means that x minus 3 has to be a factor. So I absolutely, guys, please mute yourselves. Okay, I'm getting a lot of noise. Okay. I don't need to change screen and then mute everybody. Just mute yourself. So I know I have an x minus 3 there. I know I have an x minus 3 here. How do I know that? Because 3 made my numerator equal to 0. So I know this one, and I know this one. Even if I'm not good at factoring, if I have one of the factors, usually it's easier to find the second one. Aha. So that means that I can factor and cancel. Now, I still can't evaluate it at 3 because it's still an indeterminate form. But I can cancel. Now, this is the part where a lot of folks have trouble reconciling what we're about to do. And this is really huge. And I want to make sure, because we're in Calc 2. We can do things Calc 1 people can't do. So I have a quotient, I factored and canceled, and now I have a different quotient. Is my original quotient equal to this quotient? The answer is no. It's almost the same, but it's not exactly the same. But what is the same is the limit is the same, and I'll go over that in a moment. So now I can evaluate numerator and denominator at 3. So if I put a 3 on top and a 3 on bottom, the limit is 6/4 or 3/2. Graphically, what that simply means is the ordered pair 3 comma, that guy right there is a removable discontinuity. And that should sound familiar, that term. That means in the original graph, whatever this looked like, my original graph, there's a hole at that point. And that hole is where I was headed towards. So whatever my graph looked like, I don't know what my graph looks like. I'm not even that interested in what my graph looks like. I'll get out my graphing calculator if I really want to know what it looks like. But it simply means there's a point out there, you know, here's my graph, whatever it looked like. But there's a hole at this point. And as I approached from the left and from the right, in both directions, the y value approached 3/2, even though it never got there. The limit means if I could get there, where would I get to? I don't actually have to get there. In fact, I can't get there because there's a hole there. So now let's go back to the previous statement. How do I know these are equal? So let me do a little bit of algebra. Let's get in our Wayback Machine. Like we're going all the way back to remedial algebra here. In remedial algebra, I make the following statement. I write x squared minus 9, x squared minus 3x minus 2. Now we're in a baby algebra class, and I will say, reduce this, simplify this. Well, normally when you simplify a quotient, you're canceling common factors. But if I ask you right now, what is the domain of this? Well, restrictions cannot come from the numerator. Restrictions can only come from the denominator. And I think we would all agree for this quantity right here, the domain is all real numbers except 3 and -1. So the domain, you can write it like this, by the way, real numbers except -1 and 3. I'm removing them. Or in words, all real numbers except -1 and 3. Okay, great. Some people just say my domain's all real numbers, and I just can't have that. However you say it, as long as you get your point across. Now, when I factor and cancel, here's where we get into a little bit of trouble. It feels, when I factored and canceled, and I said this quantity is now equal to x plus 3 over x plus 1. If I'm looking at this, if I walk in the room right now and I'm looking at this, boy, this sure appears like this is all real numbers except -1. It appears that's the only restriction. The problem is it came from this. This quantity could not have a 3. Therefore, this quantity cannot have a 3 either. So if we were in a remedial math class, what I'd tell you to do at this point, I say, write the disclaimer. Write the disclaimer. The disclaimer is x is not 3. This quantity is equal to this quantity as long as x is not 3, because 3 is still not in the domain, even though it appears that I can do it here. Okay, because the x minus 3 is canceled out of the original problem, I have removed the appearance that x equal 3 is a problem. That's why it's called a removable discontinuity, because I have physically removed it from the problem. I still can't have it in the domain. But the beautiful thing about limits is the limit says what happens as I approach this. I never can get to 3 because 3 is not even in the domain. But as I get closer and closer to 3, my y value gets closer and closer to 6/4. So my limit is 6/4. That's how limits work. It's where am I headed if I could actually get there. Quantities approach, limits equal. Okay, that's what the arrow indicates. So this is a reminder of something we knew way, way long time ago. Okay, at one point we were really good at that kind of stuff. And there's several types of limits I want to review today. And some of them are a little harder than maybe some of the ones you remember because we want to be able to do everything. So what if I had something like this? I have the limit as x goes to 1 of, let's say, 4x cubed minus 7x squared plus 3, actually, let me, plus 4x minus 1 all over 9x to the 4th minus 6x squared. How about plus 2x minus 5? All right, I want to do this. That's a big yikes. Okay, I want to take this limit. All right, well, I did the limit as x approaches 1 because I'm lazy. See, if x is approaching 1, all I have to do is just add the coefficients, don't I? Because I'm replacing x with 1. So if I look at this guy here, clearly numerator and denominator are both going to tend to 0. Because this is a rational function. Remember, a rational function means quotient of polynomials. We've only used that term like a bazillion times so far. This is a quotient of polynomials. Oh. And if my numerator is approaching 1, approaching 0 when x is approaching 1, that means x minus 1 has to be a factor of my numerator. It also must be a factor of my denominator. So I know with absolute certainty, I know I'm going to have something like this. I know with absolute certainty that's what the fundamental theorem of algebra guarantees. What I don't know is what goes here and here yet. So how do I find those? Synthetic division. Yeah, you can do the add and subtract to the numerator thing like I showed you, but these expressions are way too long. It would be too much work to figure it out. So let's just use synthetic division. We've done that enough times. So I'd like to know if I divide my numerator by x minus 1, what will I get? So my root is 1. So I'm going to do the numerator first. So in descending order, 4, -7, 4, -1. So as I bring this down, I get 4. 1 times 4 is 4. Add -3. 1 times -3 is -3. Add, I get 1. 1 times 1 is 1. Add, I get 0. That's a good thing. Because I got 0, that means that it was factorable. That means x minus 1 is a factor. So in reverse, that's the constant, the x squared. So this is 4x squared minus 3x plus 1. Okay, no doubt, absolute certainty. Now let's do the denominator. So if I make 1 the root in descending order, now be careful, I don't have an x cubed. So it's going to be 9x to the 4th, 0, -6, 2, -5. That placeholder is critical. It will change my answer if I don't have it there. So I bring this down. 1 times 9 is 9. Add. 1 times 9 is 9. Add. 1 times 3 is 3. Add. 1 times 5 is 5. Add. If I don't get 0 in that last position, either I have an error or I chose the wrong number. But I got a 0, so it guarantees x minus 1 is a factor. Now this will be a cube. How do I know it's going to be a cube? I'm factoring a 4th power. There's my linear factor. It has to be a cube. So 9x cubed plus 9x squared plus 3x plus 5. That's where synthetic division is its most useful, is if I have a problem like this one here. So remember, we are never evaluating this quantity at 1 because 1 is not in the domain. So when I write the limit, I can write the limit now without the x minus 1. Now, when you're doing a limit, you do not have to put in the disclaimer. But in English, I always tell people, if you're wondering if what you said with your limit is valid, there's a really simple test. Cover up the word limit. Is this quantity equal to this? Yes, it is. Is this quantity equal to this? Yes, it is, except at x equal 1. So if I was doing this without the word limit, I would say this x not equal to 1. But x can't be 1. I'm not asking what happens at x equal 1. I'm saying what's happening as x approaches 1. Oh, as x approaches 1, what does my numerator approach? It approaches 4 minus 3 plus 1, which is 2. My denominator approaches 9 plus 9 plus 3 plus 5. What would that be? 26. So my limit is. So 1/13. That would be equivalent to saying the ordered pair 1, 1/13 is where the hole is. That's where the removable discontinuity is. That's the same thing. So I could not evaluate this one, but I could evaluate this one. So the moment you can evaluate your limit is when you evaluate. Now, what are the rules? Well, when you have a quotient, you can't evaluate as long as your denominator is approaching 0. But as soon as your denominator is no longer approaching 0, it doesn't matter what the numerator is doing as long as the denominator is not approaching 0. What if my numerator approached 0 and my denominator approached 10? Well, that's just 0/10. That's 0. Okay, but what happens if my denominator approaches 0 and my numerator doesn't? That means you have a vertical asymptote graphically, so it's called an asymptotic discontinuity. That one's ugly. That's where you're going to get an infinite limit, and that's not the one we're looking at. By the way, that situation is not an indeterminate form. So we're only looking at indeterminate forms today. So another problem that is similar in nature to this one, we're going to stick with 0/0 for a little bit as the form. So, what if, okay, what if I got something like this? I'll keep it simple. I've got the limit as x goes to, let's say, 16 of x minus 16, and how about 4 minus the square root of x? Just keep it really simple. Now, there's nothing about this statement that looks terribly complicated. And you go, yeah, okay, I got this one. So let me just go ahead and evaluate this at 16, except my denominator would be approaching 0. My numerator is approaching 0. Oh, okay, it's an indeterminate form. Okay, great. It's 0/0 form. Problem is, this is not a rational function. This is not a quotient of polynomials because I have a square root on the bottom. That means there's really no factorization to take place. Darn. What I really want to do is I'd like to get the x minus 16 out of the problem. That would be great, but I've got a root. So what if, and you guys remember doing this hopefully in Calc 1, what if I multiply numerator and denominator by the conjugate of the denominator? Well, first of all, is this a legal move? Yeah, because I'm multiplying my quantity by something that is equal to 1. The only thing you cannot do is you can never multiply or divide by something that can potentially equal 0. 4 plus root x can't be 0. So that's not only a legal move, it's kind of the only way I'm going to get to my goal. Now, on the bottom, I'm going to have 16 minus x. Remember, a minus b times a plus b is a squared minus b squared. So I have 4 squared minus the root squared, so it's just that. Don't distribute the top. I want to be able to cancel factors. Aha. Now, they're not exactly the same. So what if I do this? Factor out a -1 here. Is that legal if I do that? Yeah, that's legal. Now I can cancel the x minus 16s. And I'm going to have 4 plus root x on top. If you want to write the -1 on the bottom, or if you want to write -1 in front, it isn't going to change anything. Right now, there's nothing about this that presents a problem. This is not defined at 16, but I can easily evaluate this one at 16. So again, I have a removable discontinuity. When I evaluate this, it's 4 plus root 16. That's 4 plus 4 is 8 over -1. By the way, don't say the limit of -8. That would not be true. The limit is -8. So that's it. So this one presented a little bit of an extra step for us, but that really wasn't anything outrageous. I had to do a little bit of algebra. Are there any other of the 0 over 0 forms that trouble us? Oh yeah, the trig. So if you guys remember in Calc 1, all right, so let me remind you of a couple of really, really important identities that we prove in Calc 1. Hopefully your class did. And that is the limit as theta approaches 0 of sine theta over theta is equal to 1. And the limit as theta approaches 0 of 1 minus the cosine of theta over theta is 0. The first one is proved purely geometrically and then using the sandwich or squeeze theorem. If you were in my class, you remember doing this. We derive this limit. This turns out to be extremely important. And then this one's fairly easy to prove because then we can just multiply by the conjugate and manipulate and use limit properties and all sorts of cool stuff. These two, when put together, allowed us to take the derivatives of all the trig functions, because when I used the definition of the derivative, one or both of these showed up in every statement, and I could then continue. So with these as absolute facts, how did I get the remaining limits? So as an exercise, I'm hoping you guys did this in your Calc 1. You did things like this. I want then, what's the limit as x approaches 0 of the tangent of x over x? Can I find that limit? Well, the idea in this context is if I can get either one of these statements in here, then I can evaluate them. Tan x over x, numerator and denominator both approach 0, but I don't have an identity involving tan, but I can use the fact that the tangent is the sine over the cosine. So if you want to write it like this, sine x over x times 1 over cos x. Okay. And then very importantly, the limit of a product is the product of the limits. Now, if you chose to change this to secant, that's fine. It isn't going to make any difference at this point. So now I have, by the way, I can't evaluate this yet because this has to be sitting all by itself. I can't have stuff in here, but I use the fact that the limit of a product is the product of the limits. And this one, this is easy. As x approaches 0, this approaches 1 over cosine of 0, which is just 1. This we treat as an identity. This is just 1. So that limit is 1. Cool. Okay, so I can take something a little different and manipulate it. So now, what else can I do? Well, let me show you another very important limit characteristic that some people forget, because it might seem a little obscure. And that is, as A approaches B, A plus C approaches B plus C. That's the first one. Well, that seems kind of obvious. As A approaches B, then A plus a number will approach B plus that same number. So you can think of it this way. If I said as Y approaches 10, Y plus 5 should be approaching 10 plus 5. Okay, that makes sense. And also, as A approaches B, K times A approaches K times B. Oh, so if X is approaching 3, then 10X should be approaching 10 times 3. Yeah, that makes sense. Okay, that's that. Those are always true. Those two things there. So if I take a limit statement and then I manipulate the thing that's moving, I just add the same thing or multiply the same thing, it will still be valid. So let's do a couple of limits that look like that. So the first one, what if I said I got the limit as X approaches 0, keep 0 is nice, of the sine of 4x over 2x. Well, can I just say that's 1? Well, not exactly. You see, that, it's here, theta, theta, theta. Theta is my argument. It's the same theta. What do you notice here? 4x, 2x, x. They are not the same. They have to be the same in order for me to do that. So let's see. I've got sine of 4x. I don't really want to try to expand that, using different identities. That would be really difficult. So instead, let's call 4x our theta. Can I simply multiply this by 2? Well, as long as I do this, I just multiply numerator and denominator by 2. Well, what about this 2? Then what else can I do with it? The limit of a constant times a function we know is a constant times the limit. So I absolutely can pull that out of the problem. So this is now equal to 2 times the limit as x approaches 0 of the sine of 4x over 4x. And I can cancel here if I wanted to. You can do that with limits. Now, only one more thing. That's not a 4x. Oh, but wait a minute. As x approaches 0, tell me about 4x. Won't that approach 4 times 0? That's what we just said. And 4 times 0 is, so as x approaches 0, 4x will also approach 0. So I can now say this, and that was the last piece of our grand puzzle. Notice, that's my theta. That means that this quantity right here is equal to 1. That's kind of nice. In fact, any trig limit, if the limit can be evaluated, you can always evaluate it just using this kind of stuff. Okay? Everybody got that? That's kind of neat. Now, these are the indeterminate form 0 over 0. Now I want to review a little bit of the infinity over infinity because everybody has done this. But again, if you had Calc 1 last semester, you did this at the very beginning. We did the infinity limits on lecture 3. So it's been a while. So we start with something simple, again, like a rational function. And I want to remind people how to do that. So now what the limit is x goes to infinity. We're going to do 3 problems first. So let's say I've got 4x squared minus 6x over 8x cubed plus 3x squared plus 5. All right. My numerator is growing without bound. My denominator is growing without bound. That means that this quotient, we say, has the form, or this limit has the form of infinity over infinity. Well, let me just cancel the infinities and get 1. Well, I could do that if infinity was a constant, but infinity is not a constant. In fact, infinity cannot be calculated. Infinity can only be reached with a limit. Because if I said, I want you to go that way forever, well, that means infinite. You're never actually going to get there. Or I want you to go up forever. Well, you're not going to get to some place and say, okay, I made it, I'm forever. No, but the numerator and denominator both grow without bounds. So there's a very simple algebraic step that hopefully you learned. You may have forgotten, but it's something we use often in this class. And that is, I'm going to multiply numerator and denominator. Now, by the way, have your polynomials in descending order. It just makes it easier to identify stuff. Take the lead coefficient, the lead term, which would be this guy. So what you're going to do is when you have a rational function, you're going to look at the highest term in the denominator, never the term in the numerator. Never, regardless what somebody showed you. I had someone the other day do something and turn it in, and it was some of the most grotesque mathematics I've ever seen. I just said, I don't know what terrible YouTube video you watch, but this is really bad. It's really bad. Yeah, I just don't do that. Somebody showed me, well, let me show you the video in Khan Academy I use for limits. And so I watched the video they sent me. They found limits by just plugging in numbers. And if it looks like it's getting close to 1, just say your limit's 1. In other words, we're just going to guess limits. Great. In fact, in general math, just guess an answer. That's probably good enough. No, it was really, really quite terrible. If you use that technique, there is no limit you'll ever get the rest of your life because they get more complicated and you'll never be able to guess. To actually tell somebody on a video, guess an answer. Yeah, don't do that. No, use this guy, multiply top and bottom by its reciprocal. That's a legal move, but what it does, it creates a situation here that some of you may not be familiar with, so I'm going to give you a little bit of vocab. On top, I'll have 4 over x minus 6 over x squared. On the bottom, I have an 8 plus 3 over x plus 5 over x cubed. Now, these quantities are equal. In fact, they're equal for all real numbers except 0. But 0 is not really the issue. I'm having x grow without bounds, so replacing x with 0 really isn't an issue. Now, here's where we sometimes get in a little bit of trouble. We're not sure what to do with this. So let me remind you of something, a very simple notion. Let's consider y equal 1 over x. Okay. Graphically, looks something like this. Both the x and y axes serve as asymptotes, but look at the x-axis for a moment. As x grows without bound, 1 over x is getting smaller and smaller. Does 1 over x ever equal 0? No, it does not. But the difference between 1 over x and the x-axis is actually approaching 0. As x gets bigger and bigger and bigger, 1 over x gets what we call infinitesimally small. The limit as x approaches infinity of 1 over x is 0. I never get to 0. What's happening is, as x grows without bound, the limit is 0. And if I did this on a graphing calculator, the curve would appear to just disappear into the x-axis to begin with. We are all very familiar with this concept, but there's no number I can replace x with that will ever give me 0. The limit is 0. Now, with that said, we call this a transient term. And I have 4 of them in this case. These are called transient terms. These typically show up when I have rational functions. A transient term itself is approaching 0, meaning its contribution is negligible. It's getting less and less and less important. And so what that means is, as x gets bigger and bigger and bigger and bigger, what is this graph looking like? Well, the limit of a quotient is the quotient of the limits, and the limit of a sum is the sum of the limits. It's equivalent to me taking this limit and putting it in front of this term, this term, this term, this term, and this term. These 4 terms, and we usually just go like this, they all approach 0 because they're transient terms. 8 is just 8. So my numerator is clearly approaching 0. My denominator is approaching 8. Therefore, the limit is 8. Now, the other way you could argue this in Calc 1 is you said, well, the degree of the numerator was smaller than the degree of the denominator. That means as x grows without bound, this is x-axis is acting like an asymptote. That's what that means, quite simply.
Shouldn't it equal 0, not 8?
Oh, sorry. Thank you. 0. It equals 0 over 8. Thank you, which is 0. Yeah, I said 0 and I wrote 8. The top is approaching 0. The bottom's approaching 8. Thank you. Now, what that means is the x-axis is acting like an asymptote. If you brought this up and you graphed it, it doesn't matter what's happening in close. If I go out forever and ever and ever, my graph is going to just basically disappear into the x-axis. Now, it is perfectly correct to use the degree argument, but I have to remind people you can only use that if it's a rational function. We're going to be dealing mostly with things that are not rational functions. So therefore, like a square root, there's no degree. So that won't exactly work the same way. Now let's do another one. I'll keep them similar because, again, this is review, but it's review of stuff that I'm guessing nobody's done recently. And there's some things that we may have actually forgotten. And I want to show you because it's the next couple chapters we get to, this stuff, this kind of thinking comes really huge. All right, let's try another one. What if I now have, let's say 8x to the 4th minus 6x squared. I'll keep the number of terms small. And then 2x squared plus 5x plus 1. All right, great. Now, once again, we take the lead term in the denominator, not the numerator. By the way, if you took the lead term in the numerator, you would get that the limit does not exist and the limit does exist. In this case, if you took the lead term in the numerator, you would get the limit does not exist in both problems. And you say, well, I don't understand what just went wrong. Yeah, it's because we looked at the wrong thing. It's got to be that one. And the reason it's got to be the bottom is you need your denominator to approach a constant that isn't zero. If you create a scenario, your denominator approaches zero, then you messed it up. It's not that type of indeterminate form. So I'm going to multiply top and bottom by this and do the exact same thing we just did a moment ago. And then here I'm going to have 2 plus 5 over x plus 1 over x squared. Now, just like before, that's a transient term. That's a transient term. They both go to 0. That means as x grows without bound, my denominator is approaching 2. But what happens? What's happening to my numerator? It's growing without bound. So that means my quotient is getting infinitely large. The term without bound is a common math expression. Unbounded means if something's bounded, that means there's actually a horizontal asymptote somewhere. And we do have that situation occur. But if I'm unbounded, that means it just goes up forever and ever and ever. This is unbounded, so the limit is infinity. My denominator is approaching a constant. My numerator is growing without bound. So the answer is infinity. There's no more work to perform. Oh, okay. Now, in Calc 1, we said, oh, the degree of the numerator exceeds the degree of the denominator, therefore it's going to grow without bound. But this is how we actually show it. That was something we remembered as a rule because we proved it first, and it was a nice shortcut. I love using shortcuts. We just can't always use shortcuts, all right? And then we have one more case, of course, and that is where the degrees are the same. So I've got the limit as x approaches infinity of 3x squared minus 5x minus 7 over 2x squared plus 3. Okay. Now, this is the most interesting one. This is the one that we're going to study the most as we go on in the course because of its behavior. And it's interesting behavior. Again, top and bottom grow without bound, but now it kind of feels like maybe they're growing at essentially the same rate. That would be a correct way of thinking about this, because things don't grow to infinity at the same rate necessarily. So now I'd have 3 minus 5 over x minus 7 over x squared. On the bottom, I have 2 plus 3 over x squared. Now, forget the limit. That quantity is equal to this quantity everywhere except x equals 0. Okay? So now I'm in good shape. I have a bunch of transient terms. That means they will go to 0. So as x grows without bound, this quotient is approaching 3/2. So the limit is 3/2. Now I'm going to introduce a term or symbol that some of you are not familiar with. Oh, actually, I'll leave that. Let me just write y equals. It might make it easier to think about that. So this is some graph. You know, I don't have any vertical asymptotes because the denominator is always positive. It's just some graph. And as x grows without bound, the graph is going to start looking. If this was the line y equals 3/2, whatever my graph looks like, you know, maybe it's doing this. You know, maybe it's, I don't know. I don't know which side it's coming from, but it's doing something where the graph is just getting closer and closer. The 3/2, y equals 3/2 is going to act as a horizontal asymptote. Now you remember that hopefully from Calc 1. It is equivalent to the following statement. Okay. My experience in math in my entire life is almost 100% of the use of this symbol by a human being is completely incorrect. In fact, they're using it. It doesn't apply. If you've ever used it in front of a numerical value, unless you were doing Simpson's rule or tangent line estimations, you used it incorrectly. If you're doing a calculation, that's the wrong symbol. That symbol means asymptotic. That's all that symbol has ever meant for over 2,000 years. It means asymptotic. This crazy curve is asymptotic to the line y equals 3/2 because y equals 3/2 is an asymptote. It's a horizontal asymptote. These are never equal, and there's no decimal approximation associated with it. This is asymptotic to this, which means is if I use really, really large values of x positively or negatively, this quantity here can almost be replaced with this quantity here. If I replace x with a bazillion, my calculator might say, 1.4999999, or 1.501, forever. The idea of asymptotic behavior, okay, we know what an asymptote is. We know vertical asymptotes, horizontal, even slant asymptotes. But asymptotic behavior doesn't mean there's necessarily a line involved. And that's really, really an important concept that we're going to dwell on. So I'm going to give you a really simple example before we move on of asymptotic behavior. I'm going to pull out my graphing calculator in a moment to show you. Okay. If I said, let's consider the following graph. Let's consider y equals, how about, x to the fourth minus x squared plus 1 over x squared minus 1. I want to consider this graph. Now, we know this graph has two vertical asymptotes, clearly at x equal plus or minus 1. All right. Pull out my calculator here. One second. All right, so, oops, hang on, so this is too hard to do in the dark. All right, gee. All right, so what I'm going to do is I'm going to enter that function. All right, y equals. My lighting isn't that great. Make sure I got that. Okay, so hopefully you can all see this. So I'm entering this function. Okay, now I'm going to do my window. And my window, I'm going to have x go from -10 to 10. I'm going to do the preset window that we all know and love. I'll have y go from -10 to 10. Remember, a calculator generally, graphing calculator always starts with the same default window. It's usually -10 to 10 in both directions. And now I'm going to graph. Is anything coming up yet? Oh, here we go. Oh, this is cool. Now, hopefully you can all tell there's two vertical asymptotes. Vertical asymptotes don't actually show up. Not on the graph doesn't do two little dotted lines, but we know so it did something like this. And then let's see, when actually it did something like this. Okay, this is what this looked like when I did this. Again, reminder. Okay, now here's what I'm going to do. I want to step back. I want to get a little bit further away because I want to get a better view. So I'm simply going to change my window. I'm going to make it 10 times bigger because I'd like to get a better look. It'd be kind of like saying I'm going to stand on top of a tall building and look down. I'm going to go up into outer space and look down. Not quite outer space, but I'm going to make my window just a little bit wider. Okay, so I'm going to go back to window and I'm going to make my window instead of -10 to 10, I'm going to make it -100 to 100. But now, because of that degree difference between them, the y values are going to grow so much faster than the numerator is going to grow so much faster than the denominator, then the y values are going to grow way faster than the x values. So what I'm going to do is I'm going to make my y, I'm going to have my y go from -1 to 10,000. So all I'm doing, I'm making the x 10 times bigger. I'm making the y way bigger so I can get more of this. Okay, that's all I did. Something really cool just happened.
Could you hold it up a
So,
little more?
little
Oh,
lower,
sorry,
yeah.
sorry. Can everybody see what just happened? Now my x went from -100 to 100. My y went from, basically -1 to 10,000. Does that kind of look like a parabola? That's just crazy. That kind of looks like y equal x squared. In fact, it is y equal x squared. It's exactly y equal x squared. When I stepped back, I didn't step back that far. And all of a sudden I saw this. Well, what happened to the vertical asymptotes? Oh, they're still there. They're just so close to the y-axis now that I can't actually see them. Why? Because I went from -100 to 100. And they were -1 and 1. So they're so close you can't even see them. So what about the other stuff? Same thing. Why does this look like y = x squared? Because if I simply do the long division here, which is not all that hard to do, this equals this exactly. If you put this back over a common denominator, okay, so my original graph isn't a parabola, it's this. But that's a transient term that's getting really small really fast. Now, here's what you cannot ever do. You cannot take the limit of part of this. I can't say, well, let me just take the limit of this part and ignore this. No. If I take the limit as x goes to infinity, this is going to be infinity. The degree of the numerator is higher. No. What's happening is this function is equal to this function. And as x gets bigger and bigger and bigger, the contribution of this part becomes negligent. So my graph basically starts looking more and more like this, which means this thing here, that's the correct mathematical interpretation. This function is asymptotic to this function. If I said graph the original parabola and the goofy curve on the same set of axes in a really short time, you could not distinguish the difference visually because the differences are getting so small. That's the difference. And that's getting so small so fast. Now, this is probably the most important part of calculus that you haven't seen. This is called asymptotic convergence. If you've ever had statistics, Math 119, all of statistics is based on what's called asymptotic convergence. You never calculate things directly. You use this fact. For example, if I'm trying to make conclusions about a population, could be people, could be water molecules on planet Earth, whatever, I take samples. Well, samples are small relative. Oh, but as my samples get bigger and bigger and bigger, the behavior of my samples starts looking more and more like the behavior of the population. In fact, it's a limit. But if I assume my population is so big, it's practically infinite, there's a limit and I get asymptotic convergence, that as my sample gets larger, it converges towards my population. That's why statistics works. That's why you can trust conclusions in statistics. If you do it right, you can take samples and make conclusions about the big. So this concept of asymptotic convergence is part of the reason we have to understand limits. This one was easy, but this is really kind of the coolest stuff. So now let's go kind of next level, all right? So let's continue kind of in the path that we've been doing. I want to do the limit as x goes to infinity. And let's say I want to work with, how about, I don't know, how about 3x squared minus 6x plus 4 on top? That's easy enough. And on the bottom, the square root of, how about 16x to the 4th plus 3x minus 1. All right, that'll be my denominator. Oh, wait a minute. I can't use degree because the denominator is not a polynomial. Won't work. Can't multiply top and bottom by something because I got a thing in, oh man. Yet I can do this. By the way, this question is asked in every calculus book that I own, and I own a lot of calculus books. This question is explained in no calculus book I own. This is going to be a common problem that comes up. And it's funny thing is, I've never seen a calculus book even attempt to explain this. There's only one way to do this, and it's the math we just practiced, not any math you're going to learn in the future. So what I'm going to do, I'm going to start with the denominator. 16x to the 4th plus 3x minus 1. I want you to factor out x to the 4th. Can you do that? Yeah, that's a piece of cake. We were just basically doing that a minute ago when you multiply top and bottom by 1 over x to something. This is kind of like saying multiply by 1 over x to the 4th. Well, I'd be left with a 16 plus 3 over x cubed minus 1 over x to the 4th. Now, hopefully you have no doubt that these are equal. Okay. Oh, then what's the square root of this? And the square root of this. And the square root of a product we know is the product of the square roots. Square root of x to the 4th, I can write that like this. So this is a major, major algebraic step. So I can say with absolute certainty, if I can fit this in here, I might have not have left myself enough room. This is x squared times 16 plus 3 over x cubed minus 1 over x to the fourth. Okay. What about the top? Can I factor out the x squared on the top also? Huh, let's do that. Let's take that. And I actually want to factor out the x squared. What would that leave me with on top? 3 minus 6 over x plus 4 over x squared. And there's no root, so that one's pretty easy. Okay. Haven't done anything really incredible. I just said, let's factor the top and the bottom, and we did. And hopefully you recognize I have a common factor. Can I cancel the x squared? Of course I can cancel the x squared. You can always cancel. The only time that might be an issue is if x could be 0. X is growing without bound, so I definitely can cancel those bad boys. All right, so this is now equal to 3 minus 6 over x plus 4 over x squared over the square root of 16 plus 3 over x cubed minus 1 over x to the fourth. Now let's stop for a moment, take our breath. I said the ultimate litmus test when it comes to limits. If you cover up the word limit, is this quotient equal to this quotient? Yes, it is at all values except x equals 0. But I'm approaching infinity, so I'm not really worried about the 0. And is this problem equal to this problem? Yes, they're exactly the same because x can't be 0 in this problem anyway. So now if I throw the limit, I know this is valid. So you notice what you have at this point. You have a whole bunch of transient terms. And when I take that limit, all of my transient terms will approach 0. But I don't touch the constant terms. So this is 3 over root 16, which is simply 3/4. Graphically, it means that whatever this looks like, I have a horizontal asymptote y equals 3/4, because as x grows without bound, this curve will disappear into that horizontal asymptote. That's what this tells me. Now remember, I still could have gotten 0 as a limit. I still could have gotten infinity as a limit. Everything's fair game. We got 3/4. Now, a lot of you can use a little common sense and say, you know, this is not a polynomial, but I am taking the square root of, something where the lead term involved in x to the fourth. So it behaving like an x squared is not that far-fetched. By the way, it doesn't behave like an x squared because I have square roots in there. But the whole idea of, in your mentally thinking, it's kind of like an x squared, that's an x squared. I think I can pull this one off. So if that exponent had been bigger or smaller, I think I would have had a different result, but I would have attacked it exactly the same way. So I love this problem. This one is asked in the textbooks, but never shown. And what I'm showing you is how you solve. There isn't an alternate method. At this point here, you could have said, well, how about if I multiply top and bottom by 1 over x squared? Same thing. That's not different. Now, one more type of problem I want to look at. This one is probably the most taxing for people. And just so you know, this is a question on my Calc 1 exam that's coming up. Okay, so my Calc 1 students have learned how to do this one. You just haven't done it since. Now, what happens if I have the situation where I have the infinity minus infinity form? That one can be very interesting. So what if I had something like this? I've got the limit as x goes to infinity, and I'll keep it really simple. Let's say I've got the square root of 9x, how about 9x squared plus 3x, and I want to have minus 3x. I'll keep this really simple. Now, as x grows without bound, and that's the key, x is unbounded. Clearly, this term is growing without bound. It's getting infinitely large, and so is this one, but I am taking the difference. Well, can I just try plugging in numbers? Well, the problem is I'm asking the limit to infinity. So if you plug in numbers, you're always going to get a finite value, and finite values don't equal infinity. They don't even necessarily suggest infinity. So what the heck do I do here? Anybody want to try? Anybody got suggestions? What can I do here? Just if you didn't know anything else, algebraically.
multiply by the conjugate, maybe?
I love that idea because even if it doesn't work, it's not wrong. So what if I took this quantity here? And by the way, when we say multiply, we always mean numerator and denominator because I want it to still be equal to 0. And here's why this is such a brilliant suggestion. Not because it's still going to be true, but on the top, I will have gotten rid of all of the roots. And I might be able to combine terms and simplify something. But no, I have roots on the bottom. Yeah, but the bottom is not approaching 0. See, the problem is that's approaching infinity, and I'm subtracting them. So I can't do anything with that. That's approaching infinity, but I'm adding them. So this may end up looking more like the previous problem. So what do I have on top? A minus b, a plus b. So I have the square of the square root, which is just that, minus the square of 3x. Ooh, that's kind of good, isn't it? And then my denominator is 9x squared plus 3x under the root plus 3x. Now, let's take that term right there only. If I have 9x squared plus 3x, let's factor out the x squared because I want to be able to factor and cancel and do stuff. Okay, let's take out the x squared. So that would be x squared times 9 plus 3 over x. Since it was all under the root, this is all under the root, which means this is now absolute value of x. Technically, that is absolute value of x, but my x is approaching infinity. So I can drop the absolute value because I'm only dealing with positive values. The absolute value would only be relevant if x was approaching negative infinity or any negative value. Okay, so what I have here, by the way, I haven't actually done any limit yet. I'm just manipulating the algebra. So right now on top, I have 3x. On the bottom, I have x times the root of 9 plus 3 over x plus 3x. You should really like this. X, x, x. It is correct to factor and cancel, but that's going to take exactly 2 steps algebraically. I'm too impatient. I'd rather get the answer in 1 step. You see, one thing you guys are never shown, when you have a quotient, factoring, and then that's 1 step, I rewrite it factored, and then the next step, I rewrite it with the factors canceled. That's absolutely correct. It's never the wrong thing to do. But if I simply multiply both, the thing you would have factored out was the x. If you do this, then you have the answer in 1 step, not 2. And I'm a big fan of 1 step versus 2. So rather than factor the x, take a step, rewrite the whole problem with x factored, then rewrite the whole problem with the x gone. Just do this. Now my top is 3. My bottom is the root. A lot of people don't realize some of the algebra that they can do. This quantity is equal to this quantity, except perhaps at x equals 0. But x is growing, so I don't really worry about x equals 0. So after all of that, this original statement right here, algebraically, is equal to the statement right here, except perhaps at x equals 0. Is that a good thing? That's a great thing. That means my original limit is equal to the limit. You notice I never said the original problem was equal to this. This is my scratch work. This is equal to this. So the limit of this is equal to the limit of this, which is what I'm going to write now. Actually, I don't need brackets. It's a quotient. I've already got it covered. So 9 plus 3 over x plus 3. Now, do I get into any trouble here? Well, I do have one transient term. That's going to 0. The reason I get into no trouble is my denominator is a sum. If I messed up the algebra somehow, if somehow I messed up the algebra and I had a difference here, I'd be back in the same boat as I started the problem. I'd have a denominator that, is infinity minus infinity, something evil. Okay. My numerator is 3. My denominator is approaching √9 plus 3. So my limit is, well, that's 3 over 3 plus 3, and that's just a half. Beautiful. Now, this one here, that is tricky because, again, this is how you do it. There aren't, you say, well, aren't we learning more limit techniques? Not for this. No, this is how you do it. Though this stuff here I'm showing you, this is how you do it. There aren't any tricks. There's no new things we're going to learn that will allow us to do that. This is just basically factor and cancel kind of stuff, but I'm factoring things out of a root. So it's just a little more complicated. Now, I put a limits worksheet on Canvas, but a lot of the problems we have not addressed yet. So I don't think it would be a good idea to try to attack it yet. Wait till we're finished with the limits, because again, there's a significant number of problems that you haven't learned the technique for. You have the exponential limits, you have all the weird ones that we haven't addressed that we will over the next couple of classes. All right, so that is our